Welcome to this lecture. In this lecture, I am going to discuss a problem. The problem is that we have to show that the three Pauli matrices together with 2 by 2 unit matrix form complete basis of the complex vector space of all 2 by 2 matrices, right? So this problem contains or split it into two parts. So to show this, we need to prove that first part, that sigma i's are linearly independent. Here sigma i's represent sigma naught, sigma 1, sigma 2, sigma 3. Here sigma naught is the identity matrix, and sigma 1, sigma 2 and sigma 3, these are the Pauli matrices. And in the second part, I want to show that every complex 2 by 2 matrix can be written as a combination of sigma i's. Mathematically, if I try to look at it, that means in the first part, I want to show that A naught, sigma naught, A1, sigma 1, A2, sigma 2 plus A3, sigma 3 is equal to 0. If all A naught, A1, A2 and A3 are 0, this is the condition of linear independence. And in the second part, I want to show that if C naught, C1, C1, C2 and C3, these are the complex numbers, then C naught sigma 1, C2 sigma 2, C3 sigma 3, sorry, it's not, sorry, it is 1, and it is C naught sigma naught. Let me correct it. It is 1, right? So it is 1 and it is 1, and it is equal to any matrix of 2 by 2 order, right? That's what I want to show here in the second part, right? So let me try to prove this first part here. And in the summation form, this can be written as ai sigma I, where I varies from 0 to 3. This is the short notation for this. So that means this part can be written as like this. This is A naught, sigma naught, A1 sigma 1, A2 sigma 2, A3 sigma 3, where this sigma naught is 1 0 0 1. This is the identity matrix. Sigma 1 is equal to 0 1 1 0, and sigma 2 is equal to 0 iota, 0 minus iota and 0, and the sigma 3, it can be written as 1 0 0 minus 1, right? So these are the various Pauli matrices. This is the identity matrix. These are the three Pauli matrices. So if I put these values here, then this part can be written as let's say not 0, sorry, it is 1 0 0 1 plus A1 0 1 1 0 plus A2, it is 0 minus iota iota and 0 plus A3, and it is 1 0 0 minus 1. Now if I simplify this matrix, then it can be written as A naught A1 minus iota A2 A1 plus iota A2, and it is minus A3. So this was the matrix which we are getting. Now this summation ai sigma I varies from 0 to 3 is equal to a naught a1 minus iota a2 a1 plus iota a2 minus a3, and it must be equal to 0 if and only if, means this is possible if all ai's are 0, that is a naught is equal to a1 is equal to a2 and is equal to a3, and which is equal to 0. So that means these sigma i's are linearly independent. So that means we have proved the first part. Now let us try to prove the second part. So for second part, what we want to do, we want to do that any matrix can be any matrix can be expressed as a linear combination, as a combination, not linear but simple combination. It's only combination of sigma i's, right? So for this, consider a 2 by 2 order matrix M, and let me assume that this can be written as C naught sigma naught, C1 sigma 1, C2 sigma 2, C3 sigma 3, where the C naught, C1, C2 and C3, they are complex numbers. So that means, let me consider a general matrix whose elements are M1 1, M1 2, M2 1, M2 2. This is the general matrix. Now it can be expressed as we have assumed that 1 0 0 1, C1 0 1 1 0, C2 0 minus iota iota 0 plus C3 1 0 0 minus 1. That means this can be simplified to C naught plus C3, C1 minus iota C2, C1 plus iota C2, and it is C naught minus C3. And let me call this as equation number 1. So let me try to understand this by taking an example. So consider an example, or consider a matrix M. Say this matrix is, say it can be expressed as 2 3 plus 4 iota, and it's 5 and it's 6, and as I know from equation number 1 that this can be expressed in the form of C naught plus C3, C1 minus iota C2, C1 plus iota C2 and C naught minus C3. So that means this element is equal to this element is equal to this, and this element is equal to this. So corresponding elements must be equal. If this matrix can be expressed in this manner, that means C naught plus C3 is equal to 2, C1 minus iota C2 is equal to 3 plus 4 iota, C1 plus iota C2 is equal to 5, C naught minus C3 is equal to 6. Let me call this as equation number 2, equation number 3, equation number 4, and equation number 5. Now, if I add equation 2 and 5, means addition of equation 2 and 5 gives me what? It gives me C naught is equal to 4, C3 is equal to minus 2, and similarly 3 plus 4 gives me that C1 is equal to 4 plus 2 iota, and the C2 is equal to minus iota minus 2. So if I use all these values, then C naught sorry 1001, C101 10 plus C2 0 iota minus iota 0, and it is plus C3, it is 100 minus 1, and if I put all these values as I obtained above, so it is 4, it is 1001 plus 4 plus 2 iota, it is 0110 plus minus iota minus 2 into 0 minus iota, iota and 0, minus 2 into 100 minus 1, and if I simplify this, then this can be written as 3 plus 4 iota 5 and 6, and this is nothing but this is equal to given matrix M by matrix M of order 2 by 2. Hence it is verified. Hence verified that every matrix or the given matrix can be expressed as a combination of sigma i's, that is Pauli matrices along with the unit matrix. So that's all for this lecture. In the next lecture, I will try to solve other problems of quantum mechanics which are important from examination point of view, and thanks for watching this lecture.